Welcome to another ELS tutorial video. In this video, we will demonstrate the new procedure for applying loads to structural components using the new loading scenario dialog box. In previous iterations of ELS, loads were directly assigned to elements. To improve clarity and usability, ELS version 10 and later versions will employ a new procedure for applying loads by creating groups of elements for each loading stage and assigning loads to these groups. This offers more flexibility and ease to later change the elements assigned to each group, as well as the load conditions assigned to these groups of elements. The group feature also allows for experimenting with different loading conditions by activating and deactivating groups in any desired combination, without the need to repeatedly erase and rewrite all the loading specifications for every analysis cycle, which naturally saves the user a considerable amount of time during the modeling process. This video will provide an overview for the process of creating groups in different loading conditions, as the process is the same for nearly all loading scenarios. Some notable exceptions are earthquake loads, which apply the load to the entire problem as some function of time in the three global directions, as well as blast loads, which apply the pressure weight from the blast automatically based on the bomb position and weight. Also excluded from the list are special loading cases like open foam loads and dynamic synchronous forces loads, which use the ground reaction file obtained from the analysis of an ELS problem as input in another ELS problem. It is worthy of mention that this process for applying loads has also been expanded to applying boundary conditions, elastic boundary conditions, and most other pre-processing actions. This video aims to provide an overview of two loading conditions, static concentrated loads and dynamic concentrated loads, and will save a more in-depth demonstration of other loading conditions and pre-processing actions for future videos. To demonstrate the process of applying loads, I have created a simple one-span structure consisting of 4 beams, 4 columns, and a slab. Let's start with adding a static concentrated load. To do that, head over to the Pre-Processing Browser tab and double-click the Loading Scenario option. Alternatively, you can click on the Pre-Processing menu and choose the Loading Scenario option from there. By default, ELS will have a single static stage, which is the minimum number of loading stages allowed in the model. We'll leave the solution type as static and the load condition as concentrated loads. Now, to add a new group of elements to this stage, we'll choose the Loads item in the left tree, which opens the Loads Properties dialog box for our static loading stage. This window will list all the groups assigned to the loading stage and will also allow us to edit their drawing settings and drawing text settings. To add a new group, click the Add button. As you can see, the table contains options for activating, deactivating, showing, and hiding the group, and lists the color of its indicator and the value of the force assigned to it. We can change the color for the group by clicking its corresponding color and choosing a different color from the pop-up window. To clarify, this will be the color of the group indicator, which is an outline around elements or region assigned to the group, and arrows to indicate the direction of the force components. From this screen, we can also change the values of the assigned force components, but to assign elements or regions to the group, we'll click the Apply button, and now you can see a new item for the group has been added to the left tree. Click on the new item to go to the group's properties window. In order to select some elements, we'll click the Select button, which activates the modeling window. In here, let's select the 4 elements in the center of the slab by clicking them and holding the Control key. When we're done selecting, let's press the Enter key to head back to the Group Properties window. In the Objects table, we can now see the name of the object that we've chosen and the number of elements we selected. Let's specify the force as 10 kips in the X direction, -10 kips in the Z direction, and a moment of 5 kip feet around Y, and click Apply and OK. As you can see, our newly created group is indicated by an outline around the selected elements, single-headed arrows for the force components, and a double-headed arrow for the moment component. To go back to the group's properties window, double-click its item from the pre-processing browser tree. The text icon opens the text properties pop-up, which allows you to toggle the text visibility, change the text color, group name, and text scale. The color palette icon opens the drawing properties pop-up, which contains options for changing the group's display mode, indicator color and size, and arrow size. If we would like to add more elements to our selection, click the Edit Selection button, which reselects all previously assigned elements, and while holding the Control key, click 2 additional elements from the slab and press Enter. Notice that the element count has increased to 6 elements. Now, let's talk about the only remaining option in the group's properties window, the load distribution criteria. To demonstrate this option, I'll quickly simplify my problem by changing the selected elements to only 4 elements and the assigned force to only 10 kips in the negative z direction. Here, the user has 3 options for distributing the assigned load. Distribute by volume divides the assigned load among all elements in proportion to their size. Larger elements get a larger portion of the load, and smaller ones get a smaller portion. In our example of a force of 10 kips, that means all 4 elements will end up with an applied force of 2.5 kips. In this other example, where I've merged 2 of the 4 elements, the larger element will end up with an applied force of 5 kips, twice the force applied to the other 2 elements, which get 2.5 kips each. On the other hand, distribute by number of elements will divide the force equally between all elements no matter their size. In the first case, with 4 equal-sized elements, every element will get assigned 2.5 kips, whereas in the second example, every element will get assigned 3.33 kips despite the size difference. Finally, choosing same value for all will assign the entered value as is to all 4 elements, so all 4 elements will get assigned 10 kips of force each, for a total of 40 kips. This is why it is very important to understand the distinction between these 3 options, as they give completely different results depending on what the user wants. Let's choose same value for all and click Apply and OK. As previously mentioned, the main process of applying loads that we have outlined so far is the same for most types of loading. Let's look at a new example of applying a dynamic concentrated load. First, we'll head to the Loading Scenario dialog box and add a new loading stage by clicking the Add button. In the solution type, we will choose Dynamic this time around and change our step division to 1 to obtain a quick first analysis result, and click Apply. We'll notice that the new stage has been added to the left tree as well as its subcomponents. Since I plan to assign a sizable enough load in this stage to cause a collapse in the structure, I'll also add a third empty stage in order to extend the analysis after the dynamic load application is complete. I'll also extend its duration to 2 seconds and change the step division to 1 as well. Let's click Apply to save these changes and add a new group to the second stage by clicking on the Loads item in the tree under Stage 2. Then click Add and Apply. To change the group data, select the group from the tree. ELS allows the user a versatile feature of assigning loads to 8-node regions instead of individual elements. This gives the user the flexibility to later change the mesh specifications for components with loads or pre-processing data applied to them without the need for erasing said data, because ELS determines the elements contained by the region and assigns the data to them during the solution phase. In order to demonstrate that, I'll click the Select button and quickly create an 8-node region around one of our girders. To do that, select the girder, click the additional menu icon, highlight Region Action, and click Generate 8-node region. Let's make sure only the 8-node region is selected. You can use the Properties tab to help with that if necessary, and press Enter. Now we can see the 8-node region is listed in the Objects table. Next, let's choose to assign our dynamic load in the X direction and use the function generator feature to add the load as a function of time. Here, the user has many options for entered data. Let's choose a linear function, keep the starting value, i.e. the y origin, as 0 and change the slope to 2 and click OK. ELS calculates and assigns the load value at every time step during our loading stage. If a different function is needed for any of the other load components, let's uncheck the X checkbox and choose a different direction, for example, in Y. Click the Function Generator button and change the function to Assign Function. Enter 1 as the value for both the frequency and amplitude. Click Redraw to replot the values, and once the desired curve is reached, click OK. To stop the load application at the final frame in this stage, I'll manually change the final values in the loads table to 0. Alternatively, we could have added another loading stage to gradually bring the load back to 0, to add another group to a loading stage. Let's click Apply to save all our current data. Click on the Loads item under Stage 2, which brings us back to the group list in our dynamic loading stage. Click the Add button to add a new group. ELS allows you to change the drawing settings and drawing text settings for all groups within a stage simultaneously. All you need to do is activate the drawing settings or the drawing text settings checkboxes and change all the options within as you would for a single group. Let's choose a new color for our group indicator and click Apply and OK. Now that we have multiple loading stages and groups in our problem, we can use each stage's loads window to activate, deactivate, show, or hide groups as desired. Let's deactivate the static load group we've previously assigned to the slab by clearing the Active checkbox and clicking Apply. Notice the red X mark appearing next to the group in the pre-processing browser tree. This indicates that the group has been deactivated, which means the ELS solver will treat it as if it is non-existent during the analysis. If you want to also hide the group indicator, let's click the Show checkbox and click Apply and OK. As with all elements of the ELS browser tree, we can show and hide the group by clicking its corresponding checkbox. Since we didn't assign any data to Stage 2 Group 2, let's delete it, so we're only left with 2 groups in the entire problem. Let's run the analysis and look at the results in the Results viewer. If we head over to the Input Data Browser tab, which is a reflection of the modeler's Pre-Processing Browser tab, we can see that the static load group in Stage 1 does not get exported to the viewer because we've deactivated it. By increasing the displacement factor to 10, we can see that although the load is significant, the structure vibrates but does not collapse. This suggests that we should perform a sensitivity analysis for the solution step division. This means repeating the analysis with a smaller time step, i.e. a larger step division, to check whether the time step is sufficiently small to yield accurate results. Back in the modeler, I'll quickly set my output file's path to a new directory so I can compare the two solutions. Now, let's reactivate Group 1 from the Loads item under Stage 1 in the Pre-Processing browser. I'll recheck the Active checkbox and click Apply. Now we need to increase the solution step division in our dynamic loading stage, so let's head over to the Loading Scenario dialog box, which is the topmost item in the tree, and let's change our step division to 10 and click Apply. Since our data has not changed, and ELS automatically interpolates the force values between each 2 consecutive entered data points, we will not need to repopulate the data table in the dynamic loading stage in Stage 2. Let's click Apply and OK to save these changes and run the analysis. Once the analysis is done, let's open the results viewer once more, and heading over to the Input Data tab, we can see the Stage 1 static loading group has been exported to the viewer this time around. We can tick the check boxes for both groups to show their indicators. Now, if we scroll through the simulation, we'll see Stage 1's group being applied in the starting frame, followed by Stage 2's group in subsequent frames. The structure collapses under the dynamic load as expected, and increasing the output step division beyond 10 yields similar output with an increase in the solution duration. So we can conclude that having 10 step divisions and consequently 1 millisecond as an analysis step duration is sufficient for the problem at hand and strikes a nice balance between solution accuracy and computational time. In conclusion, the new group feature introduced to ELS pre-processing actions and loading scenarios aims at granting the user full control over activating, deactivating, showing, and hiding different groups and comparing different combinations of loading situations with no remodeling or data entry necessary. The group feature, alongside the load distribution criteria options available in load groups, give the user more flexibility in modeling real-life problems and loading conditions into ELS simulations. The new feature also offers extended ease in assigning loads to structures while taking into account the constantly changing nature and conditions of loading due to future unknowns that might necessitate model changes. We hope this video has helped give you an idea of ELS's new key feature of creating loading groups and their role in optimizing the process of experimenting with different loading conditions for the same problem.